Support vector machine algorithm is used again. It's for classification as well as actual prediction, like regression. So for classification, the idea is we have two times or two datas, and we need to create a hyperplane that separates these datas or these clusters of datas. So the training of this algorithm, what we will do is we will have these two clusters of data and then draw a hyperplane that separates these datas. If the data or if the new point is on one side of this hyperplane, it will be for one cluster, and if it's on the other side, it will be for other cluster. We can see this in here, that we have two data or two clusters of data, and the hyperplane can be simply a flat plane or a flat line. In this case, we have a line because it's only 2D. So any point that is on the left of this hyperplane is going to be classified as a black point or as a black class, and on the right side of this line will be a blue point. Now the problem is, what if the data look like this? How can you create a hyperplane? Of course, you can create a circle, and you can say the points inside the circle is this much, and the points outside the circle is going to be this much. However, there is a more common point, which a more common method to be used is to increase the dimensionality of the problem by adding a kernel. The kernel takes the data points, and through an actual equation, we can create a new dimension. In this case, we have x and y, and we will introduce a kernel, which is an equation that can produce a new dimension from these points, from these data of x and y. And in our case, we choose the kernel to be x squared plus y squared. So when we calculate x squared plus y squared, we can realize that the points a little bit far from, or the more the point are far from the center, it's going to square, so it will go raise up in the z direction. That will create these points to be in here in the upper location, and the points that is in the center will stay below. And now it's easy to have a hyperplane or a hyper in this case line that can separate these points. Of course, this is going to be in 3D, so it's going to be an actual line, an actual plane that separates these points neatly. Now there are many ways or many kernels. One of the most common kernel is the radial bias function, and the radial bias function have a value of gamma, and this value of gamma will be relating the x, which is our current point, with x slash, which is the points around it, or the points in other, not around it, sorry, the other features. And based on gamma, we will calculate the kernel. Of course, there will be other math involved, but we can say that the value of gamma will affect how many points will be considered in building the hyperplane, so far or nearer points. Now, in the other hand, we have another factors, regularization parameter is called, and it's denoted by C, and the optimization will choose a smaller margin or a bigger margin. Basically, it will create a more general hyperplane, as you can see here in a low C value, or a more kind of overfitting a hyperplane that will look something like this. Of course, at the end, when you apply these methods, you have to read about the variables, and you have to try to understand as much as possible about how to handle these variables and what is the implications. Now, of course, what we talked about until now is a hyperplane and a classification issue. Now, if in reality, or what we care about is the regressor. Of course, if your problem is classification, then this is how it works. Like, you have a hyperplane, and it will separate the classes into each other. Now, in our point, or in our work, we're doing the regression. The hyperplane is actually the regressor model. So what will happen is we have these points, and we have many dimensions, and we are going to build this hyperplane around these points to predict our value. So the hyperplane is actually the most important thing, and it is kind of the generalization that we need for our data. As we get back to our coding, what we will find is the actual coding of these methods, or different machine learning algorithms, are more or less similar, in which we always call the library of our machine learning method of interest. So in our case, from sklearn SVM import SVR support vector regressor. Of course, we can add it up there, or we just can use it here. And this, now we already took it. Now we basically take the same code we did before. That is, we have start, model, and prediction, and let's see how much it will be. So just take the same thing. However, the model will be a bit different. So from here, so SVR kernel here. The kernel is what we described in the lecture, RBF, and the C value is 100 gamma. Of course, changing these values, you might get a better results, but what happens in machine learning, at the beginning we create the most simple one, so you can kill the k-nearest neighbor, and then we do another method, the support vector machine, and then we do what we will do here is random forest, and then we start tuning these models to get as best as possible and as low as possible error, mean square error in our case. And later what we will do is, there is also other methods that we can consider, that is combining different machine learning algorithms and make them vote on what is the value. So we can use different models and then take this value based on the voting of these models, or in our case regression, so the average of these models. We can do that also. It's also there are many ways, but however, this is of course is enough to actually run it. If you get a good result, then well, you get a good result. If you not, you start changing these hyperparameters, and which is these parameters that affect the training. So hyperparameters is the parameters that affect the training process, and then you start, adding different methods and try to combine different methods together by having these votes and taking the average, but if you need it only. So now we have this model, and now we are going to fit it. So we fit the model, and as you can see now, it's a little bit more complicated than before, and it's taking more time. So before, we have the actual processing time in my computer is 0.05, nothing basically time, and here let's see how much it will take. Now we will just copy paste the other the graphs to see the results. So before, we have 562, and then from 562 we got the hyperplane thing is, well, it's quite disappointing result. So the gamma 100 we can like increase to 200, 150, see how the result, but I don't expect much. So it's not really improving. Let's see how much the result is going to be. Maybe gamma, we should maybe reduce its value a little bit. But the idea is we have to tune these parameters. But even if we get not so good result, it's okay. Sometimes different methods will have different results. Now this time is not so good. It's quite bad. As you can see here, the error is worse than before. This one is VM, this one, and we need the other one, the other graph, to see where we are actually having a good data and where we're not having good data. Of course, other methods you can other methods or other way we can do it is by shuffling our data also, and there are also these kind of methods that we can shuffle our data and train and retrain. So here we can see that in this place we have quite good results. The problem happened in these engines. Here, these engines is really causing us big trouble.